ready?
So before we begin, just a reminder, if there's anyone you would like to see speak in the colloquium, if you're a distinguished visitor or someone who would like to be a distinguished visitor, please let me or someone else in the colloquium committee know, and we'll try to invite them next semester.
Mary?
And with that said, let me introduce Bar-Natan from Toronto, who will tell us about the strongest genuinely computable knot invariant in 2024.
Thank you. So I hope you all read my title and abstract, but I want to emphasize that everything I will say continues work of Rozansky, Garoufalidis, Kricker, and Ohtsuki, and maybe several other people, and is joined with Roland van der Veen. And I should also say that it was supported by NSERC grant something, which is no longer active, but the work was done under its support, and by a grant from the Chu Family Foundation of New York City. Everything I will say follows a handout. I hope you all hold a copy. If not, there are some more in the corner over there. Also, everything, including the video recording, eventually will be, well, everything is, but the video recording will be at omega epsilon beta, which is defined to be that and is used also later in the talk. I think I already talked about the acknowledgement, and part of my title is strongest genuinely computable. So let me explain what I mean by these words. So first of all, strongest. So there is some standard listing of knots with up to 19 crossings. By now the listing goes. But in particular, there are 249 knots with up to 10 crossings, and then 300,000 blah, 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 blah knots with up to 15 crossings. And the list goes a little bit further beyond that, but I didn't print it. And just as a measurement of how strong an invariant is, I'm checking how many distinct values does it get on those standard lists of knots. So the pair HOMFLY polynomial, Khovanov homology, very standard pair, attains 248 values on the 249 knots with up to 10 crossings, meaning it has a deficit of 1. The invariant I will talk about today, uppercase theta, which in fact is also a pair. It's a pair of invariant delta and lowercase theta, but whereas these two are completely unrelated with each other, here delta is a step towards the computation of theta, so it really makes sense to bundle them together. Anyway, it attains 249 values with a deficit of 0. Okay? And if I go to 15 crossings, then HOMFLY and Khovanov homology taken together, and they are much less computable, as you will see, than delta and theta, have a deficit of 70,000. Theta has a deficit of 7,000, let's say. So, you know, in some sense, it's 10 times better. If you actually take all of those invariants listed here together, the deficit isn't much less than if you just take delta and theta. So if you have two knots and you want to tell them apart, that's the tool to use, it seems. You want, yes?
So are these numbers in the first column the number of isomorphism classes? Or like
yes, yes,
so,
equivalence classes.
So we have some way of separating all 313.
There are, yes. But the algorithms, the general algorithms are very exponential. And the next point that I want to make about theta is that it's genuinely computable. So here is theta on a random knot with 300 crossings. So for most other knot invariants, if you say 300 crossings and then you say the word compute, you're in science fiction. Okay? But what do I mean by this is the invariant of a 300 crossing knot? What I mean is, theta, as I said, is an ordered pair. delta is a one-variable polynomial, and lowercase theta is a two-variable polynomial. If you have a one-variable polynomial, it's really just a list of coefficients, and I'm not showing you the coefficients here. I'm only telling you, I'm only marking this list as a sequence of colors, red for positive coefficients and blue for negative coefficients. And for this particular note, it's pretty dull. It's only alternating. This is delta, the barcode. And I also indicate the magnitude by brightness. You can barely see it, but it tends to taper off at the edges. The magnitude of the coefficients goes lower. On the other hand, theta is a two-variable polynomial, so it has a two-dimensional array of coefficients. A two-dimensional array of color, I convert them to colors using the same scheme, and then you get a picture, or a QR code if you wish. So you get a pair barcode and QR code. And this is the QR code for that random 300 crossing knot. And on the basis of this and several other examples, I also want to argue that theta is fun. Because, well, you see, I mean, there is not a lot to see in a barcode, but pictures are much more fun. And, you know, this particular picture, I have no clue why. And in fact, this seems to be the case for all large knots, or all generic large knots. The picture looks like, Mary, what is it called when you put a sand on a plate and rattle it?
Cladney.
What?
It's a Cladney plate where
Okay.
you see the nodes. But
No. When you rattle the plate and you get diffraction patterns.
Oh, that.
I was sure you would know. But anyway,
Sorry, since you called on me, why the hexagon?
Why the hexagon? I'll talk about it later, because I'm actually drawing the coefficients not using a rectangular array, but using an array whose coordinate system is a bit, angled.
So should we only be looking at 1/6 of that picture?
If you want, you can. No. These are the full coefficients, but there is some hexagonal symmetry to it. Okay? Here are some more. So here are random knots with 50 to 73 crossings. So the pattern just begins to emerge of these diffraction patterns. Again, I have no clue why it exists, but it's there. Here is the list of all knots, the 249 knots with up to 10 crossings. So you will see here lots of patterns, and you know, if you just look at one variable polynomials, there's nothing to see. And I'm just making the case that this is fun. So you'll see here lots of patterns. You'll see this ring and this double ring and this triple ring and so on. And most of these patterns, I have no idea where they're coming from. Okay? Here are some torus knots. So these are torus knots, knots drawn on the surface of a torus. And these are their invariants. Again, I'm only making the case that this is fun. And in particular, this is the 22/7 torus knot drawn here. And this is its invariant, a barcode and a QR code. That's all I want to say about fun. I also want to say that theta is meaningful. So there is something called the genus of a knot. And that's one of the first topological things to ask about a knot. What is its genus, as opposed to just separating knots. And theta gives a genus bound with absolute certainty, even though it's not proven yet. Basically, the evidence is so strong that there's just no way it's false. And we hope, with good reasons, which I will not mention today, that it will say something about ribbon knots eventually. So it has topological significance, and if these words don't mean anything to you, it doesn't matter, because that's not the story I want to tell today. Okay? So now I want to tell you about how to define theta and how to compute it. Okay? So first of all, conventions. So T, T1, and T2 are variables, just indeterminates. And T3 is defined to be T1 times T2 from this point on. Okay? And I want to tell you how to compute theta. And the first step is preparation. So if you have an n crossing node, you draw it as a diagram in the plane in which you cut it open. So here is an example. And you put, and you make sure that at all interesting places, the arcs are oriented upward. So what do I mean? In the beginning, at the entry point to the node, the arc is oriented, the orientation is up. At the exit, the orientation is up. And also, at all crossings, the two strands are oriented up. And then you label this diagram with two labels. So one label is just a running index. So 1, 2, 3, 4, 5, 6, 7. And in general, it runs up to 2n plus 1 if the node has n crossings. The second label is the following. So you see all the edges of the diagram. An edge is something either from an endpoint to a crossing or between two crossings. So all the edges begin and end oriented up, which means that if you trace the edge, the tangent starts oriented up and ends oriented up, which means that it does a certain number of rotations in the plane, a certain number or in the circle, okay? So call this rotation number phi sub k, where k is the serial number of the edge. So here, all of the phi sub k's are 0, 0, 0, 0, 0, except phi 4, because edge number 4 starts oriented up, turns clockwise one time, and then returns to being oriented up. That's preparation. This is before anything else. Having said that, I'm switching topics, and I want to tell you a little bit about traffic rules on a node diagram. So cars can drive on node diagrams. This is Model T traffic rules. Later we will have Model T1 and Model T2 and Model T3. But anyway, cars, when they drive on a node diagram, they always follow the orientation of the diagram, so they will always drive forward. And then there are 2 or 2.5 rules that governs what happens when they come to an interchange. So when a car comes to an interchange from the understrand, it just continues through. When it comes to an interchange from the overstrand, then with probability t, it continues through, and with probability 1 minus t, it drops down to the lower strand. So if the car enters here, then with probability t, it comes out here, and with probability 1 minus t, it will come out here. If the car enters on the lower strand, then with probability 1, it will exit here, and with probability 0, it will exit here. Okay? Now, if you've ever driven, you know that roads occasionally have on them traffic counters, so these black wires that go across the road and that are used to measure traffic. So basically, if you put a traffic counter here and you inject traffic here, then this counter is going to measure 1 minus t. Okay? This is for positive crossings. Maybe I don't want to define positive crossings and negative crossings. There is some right-hand rule. This is right hand, this is somehow left hand. It doesn't really matter, but the point is that for negative crossings, it's exactly the same. So if you go under, you pass through with probability 1, and if you start over, you get through with probability t inverse, and you drop with probability 1 minus t inverse. And you may complain that t and t inverse cannot be probabilities at the same time, and that's fine with me, because, you know, I'm not going to interpret it as a probability between 0 and 1 at any point. I'm only going to use the algebraic rules of probability theory. So independent events multiply, and sometimes you add probabilities, but I'm not going to actually use these aren't really probabilities. I'm just imagining that they are. Okay? And then there is the final thing, when you come to the end of the knot. So when you come to the end of the knot, there is a cliff, and all cars fall and disappear. Okay? And now I can make a crucial definition. So the traffic function, also called the green function or the two-point function of a knot, or also denoted uppercase G, which is really a matrix whose entries are G alpha beta, is the amount of traffic that a counter placed at beta, so you place a counter at beta, and it's the amount of traffic that the counter placed at beta will measure if traffic is injected on alpha. Okay, so it's a 2n by plus 1 by 2n plus 1 matrix. And by convention, not important, I could have used the opposite convention, but by convention, if alpha is equal to beta, so if the injection point and the counter are on the same strand, the same edge of the diagram, then the counter is after the injection point. Okay? So this is model T cars, and likewise there is model T nu cars, where nu is 1, 2, or 3, and everything is the same except the probabilities are replaced. Instead of T, it's T1 or T2 or T3, and then you get the matrix G sub nu, or whose entries are lowercase g sub nu alpha beta. Otherwise everything is exactly the same. Example, oh, I think I should have done it here. So let's figure out the traffic matrix for this knot diagram. Never mind that it's trivial. It's trivial so that we would be able to do it easily, okay? So if I inject traffic at edge number 1, then the counter on edge number 1 will measure 1. The counter on edge number 2 will measure something interesting. So first of all, that one car goes through, and it gets counted, so it counts 1. But then the car continues, and then that's an overcrossing, so with probability 1 minus t, it drops down, and then this counter will also measure another 1 minus t. But then it continues, and it may drop down a second time, with probability, and the probability for dropping down a second time will be 1 minus t squared. And then it measures one, so the counter will measure an additional 1 minus t squared. And then it continues, and it's a geometric series, so a counter placed here will measure sum over p times you drop, 1 minus t to the power p, and this is again a geometric series whose sum is t inverse. Finally, a counter placed on edge number 3, well, all the cars eventually exit, and exit only once, so a counter placed here will measure 1. Now, if the injection point was on edge number 2, then this counter will never measure anything. For the second counter, it's exactly the same as before, and likewise for the third counter. And if you inject the traffic on edge number 3, then the first two counters measure 0 and the last one measure 1. So the overall traffic function or traffic matrix is the matrix 1 T inverse 1, 0 T inverse 1, 0, 0, 1. It's written here. Is this okay? This is the key point. Are you okay with it? Or one of the key points. And oops, sorry, don't look. And here's the main theorem. So remember, for me, a crossing, or let me just say that for me, a crossing in a knot diagram is just a triple of numbers. So S, which is a sign, the crossing can be either positive or negative, and then the indices of the two incoming strands. the outgoing strands, this one will be I plus 1, this will be J plus 1. I don't need to indicate them. So there are two incoming strands, the upper one, which I will call I, and the lower one, which I will call J, and the same for negative crossings. The upper one is called I, the lower one is called J. So, if you have a crossing C, which is Sij, and a crossing C0, which is S0, I0, J0, and C1, which is the same, then the theorem says that there is a quadratic function, quadratic in the entries G nu alpha beta, where alpha beta belong to the, so are either I and J. So this is R11 of a crossing C, and the alpha and beta must both be either I and J. So basically, these are functions that measure how much traffic there is if you, or how much do you read if you inject the traffic here and count it here, or inject it here and count it there. Okay? So there is a quadratic function in these G nu alpha betas with coefficients that are rational functions in all of our variables. And then there is a cubic function in the parameters of the two crossings, C0 and C1. So cubic function in the G nu alpha beta, where alpha and beta belong to I0, J0, I1, and J1. And then there is also a linear function, which is less interesting, such that the following strange combination is a not invariant. What is the strange combination? So it's a normalization constant, not constant, a normalization thing, which I will describe later. And in fact, it's an invariant even without a normalization, so you can forget it. And the thing itself, the thing being computed, is the sum over all crossings of the function R11 evaluated on C, and then the sum over pairs of crossings of the function R12 evaluated on the pair, on the pair. Sorry, I wrote here theta, I meant R12, typo. Okay? So it's a sum over crossings plus a sum over pairs of crossings plus a sum over edges of the non-interesting factor. Okay? How hard is this to compute? So once I've computed the G alpha betas, and I'll describe that in a minute, this is practically trivial. So this is a sum over crossings. If you have 300 crossings, it's a sum over 300 terms. This is a quadratic time computation, or a quadratic number of operations, which is still easy if you are a computer. And this is again linear, so this is not so hard. Before saying anything more, I want to interpret these pictures a little bit. So, for example, what does the middle term measure? Okay, so it measures, well, things, so you send a type 3 car. So a type 3 car, meaning a car whose probability of dropping on a bridge is 1 minus T3. So you send a type 3 car from the vicinity of crossing C0 to the vicinity of crossing C1. And what I mean by that is that it starts either here or here. And then you measure how much arrives here, and you, well, so basically what you do is it comes here, and then it decomposes into a pair of cars, a type 1 car and a type 2 car, which travel backwards and go back from crossing number 1 to crossing number 0, and then they somehow reassemble to become car number 3. And I'm basically measuring the probability, or not quite the probability because these aren't probability, but the amplitude of this happening. Okay? And likewise, the first summand corresponds to pairs of cars that begin and end at the same crossing. And the last summand is an edge correction, a single car that starts from an edge that has a rotation number and returns to it. Okay, and I'm basically adding up all of these probabilities. Now, if the middle picture reminds you of Feynman diagrams, it's because these are Feynman diagrams. So maybe you've seen Feynman diagrams and they talk about particles splitting and this is it. And in fact, in Feynman diagrams, you do exactly the same. You sum over all positions of the beginning point and the end points. These really are Feynman diagrams, and this is made precise in some other place, but I will not talk about it anymore today. Also, this particular diagram looks a little bit like a theta graph, and hence the name of the invariant. Okay, and also hence the mistake that I made here. Okay? Are you with me? Are you okay? Good. So, I made the theorem sound like an existence theorem. There exists a quadratic and there exists a cubic. I don't really mean it. I only mean here are the quadratic, here is the quadratic, and here is the cubic, and here is the linear correction term. And I just didn't want to print them within the theorem, okay? Now, you can argue that these are immensely ugly. And you are right in some sense. They are immensely ugly. But for a computer, computers don't care. And for a computer, it's a quick computation. I mean, this is a sum of 14 or 18 or something like that terms. Who cares? It computes at no time at all. So, so it's ugly for humans, but actually pretty good for computers. Okay? Now, I want to tell you why this is an invariant. Okay? So why is it an invariant? And the first lemma that I need is that the traffic function g alpha beta is what I call relative invariant. So what do I mean by that? I mean, so if you have a knot diagram here, D is a knot diagram, it's very schematic here, and I'm measuring how much traffic there is if I inject it at alpha and measure it at beta. So I'm measuring traffic from alpha to beta. I claim that this does not change if I deform the knot, if I move the knot around away from alpha and beta. Okay? So in other words, if I take a little piece of the knot here, and within that piece, I do one of the three so-called Reidemeister moves, and these are the moves that allow you to go from any knot to any other knot. So if I do a Reidemeister 1 move, or a Reidemeister 2 move, or a Reidemeister 3 move, within that piece, which is far away from alpha and beta, then that doesn't affect the traffic. Okay? The proof is really, really easy, and I'll show the hardest case. The hardest case is the case of the most complicated of the three moves, the Reidemeister 3 move. Okay? So here is the Reidemeister 3 move enlarged. And what I'm going to tell you is that if a car enters here, it's going to come out at the top with certain probabilities. And likewise, on the other side of the Reidemeister 3, if I inject it here, it will come out at the top with certain probabilities. And these probabilities are the same. So doing the move does not change basically, if you enter anywhere at the bottom, you're going to exit at the top in the same way. And that proves this relative invariance. So let's check it. So if the car enters here, it gets here with probability t, because that's an overcrossings, and it gets here with probability t squared. Or it might go to the left, and that happens with probability 1 minus t. Okay? And or it might get to the middle. To get to the middle, it has to go through here, and then it's a probability t event, and then it has to drop with probability 1 minus t, so you get t times 1 minus t. On the right, it's more complicated. If a car enters at the bottom left, then a counter measure here, a counter placed here will measure t, and a counter placed here will measure 1 minus t. And then the traffic coming over from here is going to continue to here with probability, well, so it's 1 minus t, but it's going to continue with probability t, so you get 1 minus t times t. Or it's going to drop with probability 1 minus t squared. But there is a second way to get here, and it is to go to here and then drop down and then flow under, and the probability of that is t times 1 minus t, so it's t plus, so you add t times 1 minus t. And basically you can continue the computation, and then you can use your algebra skills to verify that this is equal to that, and so my assertion is correct. That was if I enter on the bottom left. If the car enters in the middle or on the bottom right, it's even easier. Okay? Are you still with me? Okay. The second property of the traffic function that I need is the so-called G rules. And the G rules are essentially empty. So let me tell you what they are. Okay? So suppose you have a crossing. I didn't indicate the sign is S. The lower strand is I, the upper strand is I, the lower strand is J. Therefore, the exiting edge on the lower strand is J plus, and the exiting on the upper is I plus, where I plus and J plus are shorts for I plus 1 and J plus 1. Okay? Then I claim that injecting the traffic at J and measuring at beta, where beta is anywhere else. So, you know, beta could be here. Okay? So injecting the traffic at J and measuring it there is the same as injecting it at J plus and measuring it at beta. Obviously, because the traffic rule was that if you enter at J, you continue to J plus. The only difference is if beta is if the measuring point is on edge number J. Because then if you inject on J, then the counter placed here will measure it, but the counter but if you inject on J plus, then a counter measured here will not measure it. So there is a difference of a delta function of J and beta, and this is this rule. Similarly, the second rule written here is a formalization of what happens when you go on the upper strand of a crossing. So if you enter at I and measure at beta, it's the same as with probability t, or t to the s, entering at I plus, or with probability 1 minus t to the s entering at j plus, but there is a correction term, and this is a delta function of I and beta. Likewise, and finally, there is a rule which says that if you inject the traffic on the last strand and measure it anywhere, well, if you inject it on the last strand, the only thing the car is going to do is to get to the cliff and drop. So the only counter that's going to measure anything is the counter which is on the last strand, so you get delta 2n plus and beta. Are you okay with this? Good. And likewise, there are G rules which tell you how to move a counter. So if you have a counter placed at I plus, you can move it to I, and there is some cost involved, and I'm not going to go through it, but it's very, very easy. Okay? So these are the G rules, and I've just proven them. And a corollary is that the matrix G is easily computable. Because this rule really say that if you multiply the matrix G on the left by some matrix A, you get the identity. And what is the matrix A? Well, you can read it off these equations. The matrix A is a matrix that looks like the 2n plus 1 by 2n plus 1 identity matrix, but with additional contribution. So for every crossing, if it's an Sij crossing, then at row I and row j, and column I plus and column j plus, you add these entries. Okay? So for the trefoil knot, here's the trefoil knot again. There are 3 crossings. For example, there is the yellow crossing. And the yellow crossing is a crossing in which I is equal to 3 and j is equal to 6 and s is equal to 1. So therefore, in this matrix A, in row 3 and row 6 and column 4 and column 7, I insert a copy of this 2 by 2 gadget. Okay? So G is easily computable. All you have to do is invert a matrix. And in fact, the bottleneck for the computation of theta is inverting this matrix. If you have a 300 crossing knot, then this becomes a 600 by 600 matrix, and you have to invert a symbolic 600 by 600 matrix. That takes time, but it's still polynomial time. It's still relatively efficient. Okay, but this is the bottleneck. Okay? Now, just for fun, here is the traffic function for the trefoil knot. So G is the inverse of A. Are you still with me? Okay. One more note. The Alexander polynomial, a well-known quantity, delta, is the determinant of A up to some minor normalization. Okay? And I also set delta sub nu for nu equals 1 to 3 to be the Alexander polynomial evaluated at T1, T2, or T3. And then you see, if you look again at the formula, then this is a then the things that appear here are functions of the G alpha beta. G is the inverse of A, so it's going to have denominators, the Alexander the determinant of A. So by multiplying by delta 1, delta 2, delta 3, the only thing it does is to eliminate all the denominators. So instead of a rational function, I get a polynomial. Okay? Anyway, the last thing to do is to prove that this is an invariant. Okay? So suppose I want to show that my quantity theta does not change when I do a Reidemeister 3 move. So a Reidemeister 3 move is a move like from here to here, and I labeled all the edges for use later. So this is edge I, j, k. This will be k plus, j plus, I plus, and so on. And then I plus plus at the top. Okay? Now, the invariant is computed as a sum over crossings, or maybe a double sum. So part of it is a sum, and part of it is a double sum. If the summands are not within this picture, within that part of the picture, so basically if the summands are here and here, then for every summand where the C0 and C1 are here and here, there is a corresponding summand on the right, and the traffic function is relatively invariant, so these summands are equal. So the only thing I have to care about is the case where my summands C is here, here, or here. And the other, this is for the single summation, and for the double summation, the only thing I have to care about is if both C0 and C1 are here, are in this picture, or if C0 is here and C1 is somewhere far away, or if C1 is here and C0 is somewhere far away. So these are the only comparisons I have to make. So I get a finite number of summands to compare, and these summands involve the G function, the traffic function, at points inside here. This is for the left-hand side, or at points inside here, this is for the right-hand side, and these G's do change. But I have the G rules, and the G rules allow me to rewrite the G's inside, to push them, and rewrite them in terms of the G's up at the top. This is for the alphas. For the betas, you actually push them down. But in either case, you push the G's to outside the picture, to outside the part that changes, and then you are in the relative invariance domain. And then things don't change. So it's a finite computation. Okay, except there are 18 terms and you have to sum them, and it's a finite computation, but it's way over my IQ. So instead of doing it, I'm asking my computer to do it. Okay? So here is a Mathematica session that computes it, and you can find a full computation at this URL. So first of all, I load a list of notes for use later, and I load something that computes rotation numbers because this is a preparation, it's not really interesting. And I load something that plots polynomial as QR codes. Again, not particularly interesting. Then I define T3 to be T1 times T2, and then this is a technicality, please ignore. Something about how things are stored, how polynomials are stored. It doesn't change the mathematics at all. It's only a technicality. And then R11 is written here. It might be different, but this is just because I simplified things differently. Okay? R12 is written here. It's a function of two crossings, so it's a function of a triple S0, I0, J0, and S1, I1, J1. And finally, gamma 1 is written here. And then I implement the G rules. So delta alpha beta, delta ij is defined to be if I is equal to j, then 1, otherwise 0. And then the G rules for a crossing Sij are, well, these are exactly the rules that I wrote before. Okay? And then I define the diagram sum for a list of crossings to be a single sum over the crossings of the R11 plus a double sum over the crossings of, plus a double sum over the crossings of R12. And then I compute the diagram sum for the three crossings that appear in the Reidemeister 3 move. So 1 jk, 1 ik plus, 1 I plus j plus, and add an extra crossing for good measure. This is the crossing here. Okay? I hit enter and I ask the computer to simplify whether left-hand side is equal to right-hand side. The computer says true, and that's the proof. Okay? So, you may complain that it's high school algebra. Some sophistication will come in a few more minutes. Okay? Anyway, by the way, here is a complete program to compute theta. So A is the identity matrix, but then for each crossing of the form Sij, I add to A in rows ij and columns I plus 1, j plus 1, the matrix that I've indicated before. I let delta be the determinant of A, I let G be the inverse of A. This is where all the computation time is spent. And then I ignore the technicality, but then I compute theta, which is the evaluation of R12. I add to it the evaluation of R11 summed over the crossings, and I add to it the evaluation of gamma summed over the edges, and then I output the result basically as I promised. And here are the results of the computation. So when I compute theta for the knot 3,1, this is the trefoil knot, the knot shown right at the beginning, I get delta, which is a one-variable polynomial, and lowercase theta, which is a two-variable polynomial. And now let me tell you how I plot it. So basically, right in the middle, I plot the constant coefficient. In this case, there is no constant coefficient, so it's plotted as white. Then 1 unit to the right would be the coefficient of T1. Not there, so it's plotted as white. 1 unit to the right is the coefficient of T1 squared. The coefficient of T1 squared is negative, so it's plotted as blue. And then T2, instead of instead of using a perpendicular coordinate system, I draw T2 in the direction of the cubic root of 1. This just highlights the hexagonal symmetry. So for example, this one would be the coefficient of T2 squared, which is again -1. And this one will be the coefficient of T1 squared times T2. So where is T1 squared times T2? It's here, it's a positive coefficient, so it's red. Likewise, I'm computing the invariance of the Conway and the Kinoshita-Terasaka knots. These are famous knots because they're notoriously different to separate. And their invariants look completely different. Okay? Finally, here are again the few torus knots that I mentioned before. And I only have 4 minutes. So I'll go through the deeper stuff and the questions very quickly. So first of all, there is a similar invariant defined by Garoufalidis and Kashayev and studied by Garoufalidis and Lee. Again, it's very similar, but ours is way easier to compute. Way, way, way easier to compute, but still I don't know the relation. Conjecture, right, all the pictures you saw have hexagonal symmetry. I actually don't know how to prove it. So, I suppose in math, if you don't know something, it makes it more fun. It means people can come and participate and do stuff. Conjecture 3, this is where it all came from. And I'm not going to go in any detail on it, but there is something called the Drinfeld double of a Lie algebra. And then there is a quantization machinery that leads to knot invariant. And what we did is we took the Drinfeld double while multiplying the coproduct, the co-bracket, with epsilon and expanding the result in a power series of in epsilon. And what I told you was the coefficient of epsilon to the power 1 for SL3. Okay, starting from the Lie algebra SL3, except I'm lying to you. That's what inspired the result. We actually, carrying out the computation was actually too hard, so we didn't. We just guessed the result using the inspiration coming from conjecture number 3. But conjecture number 3 remains conjecture number 3. Then theta seems to be equal, in fact is equal with probability, close to 1, is equal to the 2-loop contribution to the Kontsievich integral, whatever that is, but we don't know how to prove it. I should say, and I mentioned it already, is that there is a perturbed Gaussian integral formula, which is a synonym for Feynman diagrams for theta. That's a discussion that occurs elsewhere. I should also say that there is a relationship with the genus, but that suggests a conjecture that there should be another Gaussian integral formula in which you integrate over the homology of a ciphered surface of the knot. I'm not defining any of these terms, but this is still an open problem, and that would be absolutely wonderful if you solve it. Also, I kind of mentioned in passing that I could have started with other Lie algebras, and I could have expanded to higher powers of that parameter epsilon. And this basically shows that there is a lot more where this one is coming from. And the higher invariants of this type, instead of involving a single and a double sum on the knot, may involve a single and a double and a triple sum. And instead of depending on 2 variables, T1 and T2, they will depend on as many variables as there are roots, not roots, as the dimension of the Cartan algebra of the Lie algebra. So, so eventually they will get too complicated to compute. Eventually, computing the triple sum of 3 variable polynomials is going to take more than inverting a matrix. It's always the same matrix to invert, but the summations will eventually become harder. But there is still room for 1 or 2 or maybe 3 invariants for which the bottleneck is the computation of the traffic function. So it's still possible that at the same computation time, we will have an even stronger invariant. Okay, dream number 9 is that, you see, at some point, Lie algebras entered the story. But they really entered by the way we discovered the story. The story in itself has nothing to do with Lie algebras. So I'm really dreaming that one day we will have an explanation for these invariants that does not involve all this quantization machinery and nonsense. And in fact, I really hope to replace the quantization nonsense with something much better. So that's dream number 9. And dream number 10 is that theta will have something to say about ribbon knots. I will not explain, but this is, again, will be absolutely amazing if it happens. And thank you for bearing with me.
Are there questions for Dror?
Does SL3 act on theta?
Sorry?
Does SL3 act on theta?
Does SL3 act on
Theta.
on theta?
No.
I don't know what it means. No. Okay, SL3, theta comes from SL3 in some way, but there isn't.
Yeah, you have a function on the polynomial, right?
But it's not invariant. Theta is not invariant under this action. Okay? Now, yeah, sorry. I should say that, invariance was proven and it's very, very easy, but even the hexagonal symmetry is still a mystery to us. Yes?
So at the beginning you said there was a pair of invariants, and I think you described the 2-variable one to us? But
No, I also described the 1 variable. So the 1 variable was delta, the Alexander polynomial. So basically, you create this matrix A, and then you invert it and do fancy stuff to get theta, or you compute its determinant to get delta. But you really want the determinant even if you are doing theta, because it's what, and it removes all the denominators. Yes?
So is theta supposed to be, I'm just guessing based on the hexagonal symmetry, that it's supposed to be something like a function, like an element of a ring of characters of a Cartan or something in SL3, or like what is, can you say what kind of object it is if it agrees with this Garoufalidis story?
It's a Weil invariant polynomial on the Cartan, but I don't have a. But that's a conjecture.
Sure. Any other questions? If not, let's thank for one more time.